Hi everyone, my name is Karago and Treasure.
My name is Humphrey Junior Mabe.
Ayan, your microphone is off.
Sorry, my name is N. Mustafa Abdurrahman.
We are presenting our project called the Multi-Modal AGI Partial Discharge Diagnostic System. This project aims to identify partial discharge, classify it, and identify the location of the partial discharge in a high voltage systems like transformers, generators, or even switch gears. The current problem we face is that partial discharge is an electrical spark that can lead to degradation of the insulation in high voltage equipment. This degradation of insulation can lead to electrical sparks that lead to equipment failure, power outages, and even can lead to fires and safety issues. The current issue is that the current maintenance practices that we have are largely reactive. They lack continuous monitoring mechanisms that can detect the early stage insulation and deterioration, especially in Africa. So we aim to solve this through extracting discriminative time domain and frequency domain features, differentiating between corona, internal, and surface discharge types, and determining the source of the partial discharge, enabling predictive maintenance through the automated PD classification. This will be done through the sensors that will capture both acoustic and electrical signal data. With the research questions aim to look at the dataset integrity, which are the datasets of both acoustics and electrical datasets, identifying the different waveform characteristics across the time and frequency, and extracting features that can be used to train models to classify and algorithms to locate where the partial discharge is happening. Our research contributions included a comprehensive data exploratory analysis of both the acoustic and electrical datasets to understand both the signal behavior and distribution patterns, to analyze the raw waveform characteristics to know the characteristics of the partial discharge, of different types of partial discharge, and different types of signals that can come from the electrical devices, and to identify the statistical properties, the noise patterns, inconsistencies, and also visualize these features. So the outputs is we got a cleaned data set, we got statistical summaries, we got the visualization plots, we identified the candidates for machine learning modeling, and also gained insight into the separability of the different types of partial discharges. Our system architecture includes a sensor layer that consists of sensors to capture both the acoustic and electrical signal data, which is the HFTC for electrical, and the microphones, MEMS microphones, to capture acoustic data. We have a neural layer that extracts the features, does the probability matching and detects the different pulses, and we have the causal layer and symbolic layer, which aims to match these insights into the physics validation, the time of arrival algorithms that locate where these signals are coming from, and rule-based inferences that will also aid in the agentic layer, which adds the explainable insights and risk assessments. And our final input will be the partial discharge type, the confidence, locations, and insights into the faults, including the risks. So our datasets, we use two main datasets, which are the acoustic dataset and electrical signal dataset. We use the acoustic dataset that was recorded through a 32-channel MEMS microphone array that captures this sound. We're able to collect files that were sampled at 96 Hz that last 50 seconds, that are repeated over 10 seconds each in each of these files, leading to 5 samples per file. These signals included the chaps, white Gaussian noise, and partial discharge signals. Ayan?
For the electrical dataset, it consists of 250 control laboratory partial discharge acquisitions that were recorded under a HFCT, whereby we had 347 files with no duplicates and sampled under 125 mega samples per second under the duration of 35 milliseconds, whereby each was categorized. And yeah, that is it, having different types and folders.
So these are the output results for the data analysis for our acoustic dataset. So we had a count of 8,640 files, wave files, in which we're able to extract these spectrograms that shows the different wave, the frequency and the time for the different waveforms. So we see that the chaps have a smaller frequency range compared to the white noise and the partial discharge waveforms, or the frequency, the waveforms, and we see that the white noise having the largest frequency range. So for the waveforms, we see the same insights or the same correlation between the spectrograms and the waveforms that we captured, whereby we see the chaps having the smallest sound envelope, while the partial discharge it's wider and ribbed in nature, which shows the unpredictable nature of these signals. For the white noise, you see that it has a higher amplitude compared to each of these signals, and this can be a feature that can be used to differentiate between the difference between the chaps, the partial discharge, and the noise that is emitted from these electrical devices. Here we have a zoomed in description of these waveforms, as you can see. So here we come across we're able to extract different features from these waveforms. These features included the energy of the waveforms, the root mean energy, the kurtosis, which shows kurtosis at the rate at which the waveform changes, which are the peaks, the crest factor, the zero cross rate, the centroid, the flatness. And from here we see there is a high correlation between the root mean square and the energy which is expected. We see also a high correlation between the MFCC, which describes the spectral envelope of the different signals. So from this correlation matrix, we're able to see the features that we're able to drop and keep. Then from the physical heat maps, we're able to see the energy received by each of the channels. You see that the energy varies from location to location, and from channel to channel. So with this variation, it shows that there will be an ease to in localizing the source of the fault. So from the frequency report, we're able to see the range, the different frequency ranges of partial discharge and the white noise and the chaps. The partial discharge showed a frequency range of between 2,000 and 15,500. And we see white noise having the largest frequency range between 4,000 and 19,947. And we have the chaps having a frequency range of between 1,000 and 10,300 Hz. So from these frequency ranges, we see that we see an overlap. We see that the white noise has the highest maximum frequency, and we can see the different overlaps between the different frequencies. And we're able to plot the different violin graphs, which we're able to show which feature can be able to differentiate each of these signals. So we saw that the centroid distribution is the strongest feature that can be able to differentiate between the white noise, the partial discharge, and the chaps. And from each of these graphs, we're able to see the strongest features that will be used in a machine learning model. We see MFCC, also see the energy distribution being a strong feature because of the different natures. And we can see, for example, the crest factor distribution having an issue whereby the violin graphs are somehow overlapping with each other. So here I'll hand over to my colleague Humphrey, who will go into the partial discharge signal.
Thank you, Treasure, for the overview on the multi-category dataset. After doing the EDA on the multi-category dataset, we dived further deeper into partial discharge as an individual, and with the graphs I'm going to describe, we're able to find certain patterns, visualize, and then these patterns help us understand certain things about a partial discharge. As you can see on this slide, the first graph we see is the spectrogram. Now, this graph shows how the frequency content of audio changes over time. The x-axis is the time, whereas the y-axis is the frequency. And the color intensity, as you can see, represents energy at each frequency and time. Notice the repeating, Notice the repeating vertical bands. Now, this indicates periodic bursts of energy, suggesting a repeating sound pattern. Now, the energy is spread across a wide frequency range, with the bright colors showing where the signal is actually strongest. Yeah, that's what the spectrogram is about. And then next up is the signal-to-noise ratio distribution graph. Now, this histogram displays the distribution of signal-to-noise ratio values. Now, most of the values cluster around -4 decibels, meaning that the noise levels in this audio or on the sound is relatively high compared to the signal. Now, if you look at the right-hand side of that graph, you can see that few samples on that in our audio have a low SNR. Now that means that generally on a waveform, that means that generally the audio has some has mostly noise, which could impact our audio classification. So if you look at, for example, since our audio is 50 seconds, in the 50 seconds, if you try and pick out the different sections where we have the bursts, you find that they're limited, and the times whereby we don't have the bursts, they're actually more. So that's what the SNR is trying to show us. And then the third graph is the mean amplitude distribution graph histogram. Now, this histogram shows the distribution of mean amplitude values across samples. The x-axis shows the mean values, whereas the y shows us the count. Now, it shows us that most values are concentrated at the lower end, indicating that majority of the audio is quiet, as I had previously explained. Now, there are a few samples with, of course, higher mean values, suggesting that occasional louder sounds or peaks occur or exist in the data. And then on the lower graph, the first one is it's just a partial discharge segment. Now it's a waveform. This waveform plot actually displays segments of audio signals over time. The blue waveform shows amplitude, while the pink background highlights detected segments. Now the variations in amplitude show periods of activity and silence, as you can see in the graphs, with the repeating patterns matching the periodic structure. So across the 50 seconds, you can see the periodic bursts and so on. And then the last graph on this slide actually is a waveform overlay. Now, this plot overlays different waveforms from multiple channels at a single location. Each colored line, as you can see there, like it's like a rainbow. So each colored line represents a different channel. The variation between the lines shows differences in how each channel captures sound, possibly due to maybe spatial arrangement or effects from the environment. The overall similarity suggests that the channels are recording the same event, but with slight timing or differences in amplitude. You can move to the next slide, please. In the next slide, we're trying to show different features in relation to our data set or our partial discharge data set. Now, the first graph is the MFCC mean histogram. Now, this histogram shows the distribution of the MFCCs, which relates to the audio. Like now, most of which is tightly clustered. As you can see on the graph, it's clustered towards the end, and this actually shows us that there's a consistent temporal characteristic that exists across the different samples. Now, the second one is a centroid. The centroid shows us where the center of mass of the spectrum actually lies. Now, most values actually lie between, according to that graph, you can see lie between 5,000 and 7,000 hertz, indicating that the energy is concentrated in the middle of the frequency. Now, the third one is the ZCR. That's a zero crossing rate histogram. It shows how often the signal changes sign. Now, most values are clustered between 0.4 and 0.6, indicating a moderate rate of sign changes, which is typical for signals with both voiced or unvoiced components. Now, the spread suggests some samples are not maybe don't have tone, whereas others are actually very noisy. And then also have the RMS histogram. It shows the distribution of a signal energy. Now, most values, as you can see, are actually low, but there's a tail towards the higher RMS, indicating occasional louder segments, as we previously discussed. Now, this matches the mean amplitude distribution and suggests the presence of both quiet and loud events. The last one is the spectral roll-off histogram, which shows the frequency. It shows that the frequency of how can I say it? It shows the frequency below which a certain percentage of energy is contained. Now, most values are clustered between 8,000 and 1,000 hertz, indicating that the majority of the signal energy is in the lower part of the spectrum with a slight bit of variation. And then we have a box plot, as you can see down there. Now, the box plot shows uh, the RMS energy for each channel. Now, each box represents a spread of values. Okay, all the boxes represent a spread of our values, with most channels having maybe a similar median, but then there's a slight variation. Now, this indicates that however much most of the channels are generally consistent, some channels actually tend to capture more or less energy, possibly due to maybe the position on the location. And then lastly, we have this is a heat map. Now, this heat map estimates a lag, yeah, in the times of arrival between locations and channels. Now, the color variation shows differences in lag, with the brighter colors representing higher lag values. The scattered patterns represent complex sound environment, yeah, with no clear dominant structure, indicating that sound maybe can arrive at different times or whatever you call it in the given array. Yeah, that's the heat map. Thank you.
Okay, thank you very much. I'm going to talk about the electrical data set, and I'm going to start with the waveform. So we're going to first start with comparing the different waveforms of the corona internal and the surface of the three folders. If you look very carefully at the corona discharge waveform, you will see that it has very high sparks. It's very continuous and it's less compact compared to that of the internal discharge, which is very smooth and very more dense compared to that of the corona discharge. But it has less amplitude, therefore less sparks, therefore less frequency compared to the corona and the surface discharge. The surface discharge is also having higher sparks at repetitive forms, but not as high repetitive as that of the corona, and it's not as smooth as that of the internal discharge, but it has less sparks compared to the other two discharges, so it has less frequency. If we compare that using the different spectrograms, if you look very carefully at the spectrogram, you will see that the corona discharge spectrogram has a wide band of frequency over time compared to that of the internal and the surface discharge. So if you look at that of the corona discharge, you will see that it has a very high band. So therefore it varies and it's not very stable. But for that of the internal discharge, it has mainly two strong bands between 2 and 3 and 3 and 4 frequencies over a given time of period compared to that of the corona discharge, which makes it more intense and more stable, and therefore it does not vary compared to that of the corona discharge, whereas that of the surface discharge shows us that for it happens more of in a vertical form, and it's less stable and less smooth kind of frequency compared to both of the internal discharge and that of the corona discharge. So that of the corona discharge it changes a lot of times, so therefore it has less frequency and more sparks, which can take us back and relate us back to the previous charts that we have had about the different waveforms above. So if we go to the next slide, we're going to talk about the different correlation diagrams for the different features. So if you look very carefully at the different features, you can see that the max, the kurtosis, and the screw have a very high positive correlation. So therefore, we might end up dropping 1 to reduce redundancy, plus they carry similar shapes. Then also, if you look at the RMS and the STD, they also happen to have a high positive correlation, whereby both measure signal energy or dispersion, and therefore we need 1 for modeling, and therefore we're going to end up dropping 1 of them. And for the negative correlation, if you look at the minimum and the RMS, they have the strongest negative correlation, which suggests lower minimum values are associated with higher overall energy. Therefore, they reflect polarity and asymmetry in discharge signals. So if we look further to the different graphs, so this mainly also helps us to reflect on the different frequencies, which show that that of the internal discharge is more distributed compared to that of the corona discharge and that of the internal discharge, whereby that of the corona discharge has a very high compact frequency ranges over the different samples, and its intensity seems to be higher, but the one that has the highest spark being the internal discharge. Then if we go to the next slide, we're going to reach our conclusion and limitations. Our conclusion being that acoustics and electrical PD datasets show distinguishable signal characteristics across corona surface and internal discharge types, whereby we use time and domain frequency features to reveal meaningful variations in energy, amplitude, and spectral distributions. The acoustic features demonstrate stronger class separability comparable to that of the electrical features alone. Then the EDA phase successfully identified candidate features suitable for future machine learning classification and localization. The limitations we faced, as previously said, is that the data sets collected were under controlled laboratory conditions. So therefore, next time we have to consider using field-acquired PD data. Then the electrical signals have extremely high sampling rate, leading to large data volumes. And also the other limitation is that limited discharge categories may risk model generalization. Then the current analysis, which focuses on EDA, whereby we haven't yet done the validation and the localization modeling, which have not yet been implemented. So our next steps will be that transition from EDA. We want to transition from EDA to specific machine learning model development and performance evaluation. We're going to optimize feature engineering using advanced time feature frequency analysis techniques. We're going to integrate acoustics and electrical datasets into multi-modal classification framework. And then we're going to implement localization algorithms to estimate the partial origin of partial discharge events, test robustness under real operational noise conditions in industrial environment. And under our acknowledgements, we are going to mainly acknowledge the IDE datasets that we used for its instructions for the acoustics and the electrical, and yeah, and then its abstractions, which led us to using the Science Direct publications, which was a paper that was released, giving us insights and methodological guidance to partial discharge analysis and signal processing techniques. And finally,